For decades, astronomers operated under a comfortable assumption. Planets were predictable. They were mostly spherical bodies with standard swirling weather patterns and orderly elliptical orbits. Then the Cassini space probe looked at the North Pole of Saturn. It found a perfectly symmetrical six-sided hexagon storm. It looked completely unnatural, turning almost as a solid geometric body across the pole. A few years later, the Juno probe sent back images from Jupiter's North Pole and found an even stranger structure. 8 massive mega-cyclones, each the size of the continental United States, were swirling together to form a precise 8-sided octagon. Stellar structures present an even larger problem. Consider Tabby's star. This distant sun suddenly experienced an erratic, massive 22% drop in its brightness. Look at this scale comparison. A massive Jupiter-sized planet passing in front of a star only blocks about 1% of its light. To block a 22% chunk of a star's light requires an object with almost impossible dimensions. A planet cannot physically grow that large. If you add more mass to a gas giant, it just gets denser, not wider. This physical limit led some physicists to a controversial hypothesis. The object blocking the light might be an artificially constructed alien megastructure. To visualize a star-encompassing megastructure on a miniature scale, scientists point to the Crescent Dunes Solar Energy Project in the Nevada desert. Thousands of reflective panels harvest energy from our sun, suggesting an advanced civilization could build a monstrous solar farm around their own star. We cannot simply send a probe thousands of light-years away to inspect Tabby's star, or dive deep into the crushing atmospheres of Jupiter and Saturn. To figure out what makes these cosmic glitches tick, we have to find ways to replicate them right here on Earth. To solve the mystery of those perfectly symmetrical storms on Jupiter and Saturn, physicists set up an elegant experiment. They used a large tank of water to represent a planet's atmosphere, and spun the center of the tank at a different speed than the outer edges to mimic a gas giant's rotation. When they injected the water with dye to track the flow, sections rotating at different speeds naturally form perfectly stable geometric boundaries. Depending on the exact speed, the fluid creates exact triangles, hexagons, or octagons. This experimental approach also helps decode extreme exoplanet meteorology. Take 55 Cancri E. This rocky planet orbits so close to its parent star that its day side is an ocean of permanently molten lava, reaching over 4,500 degrees Fahrenheit. At those extreme temperatures, the rock at the surface actually vaporizes into a gas. This vaporized rock lifts high into the atmosphere, cools, and then condenses, raining down on the planet's surface as solid, tiny pebbles. An even hotter environment exists on the gas giant WASP-12b. Here, the atmosphere is so scorching that clouds form from aluminum oxide. Aluminum oxide forms the basis of the mineral corundum, meaning the rain falling through WASP-12b's sky is effectively made of liquid rubies. By studying extreme thermal environments on our own planet, like bubbling volcanic lava lakes in Hawaii, scientists can gather the baseline data needed to decode alien atmospheric conditions that defy our standard understanding of weather. Of course, not every deep space anomaly holds up to scrutiny. In 2007, astronomers detected the Lorimer burst, an intense, mysterious pulse of radio waves that initially looked exactly like an extraterrestrial transmission. When they gathered more data a few years later, a suspicious pattern emerged. The bursts almost always occurred in the middle of the day, specifically around lunchtime. It turned out the signal was just local interference, generated every time someone opened the observatory's break room microwave door while it was still running. While the Lorimer burst was a false alarm, orbital images of Mars reveal physical features that defy simple classification. Dark streaks appear on the walls of craters during the Martian spring and summer, widening as the temperature rises before fading away in the fall. To figure out what could be causing these shifting patterns on an otherwise dry world, researchers look to one of the most arid, seemingly dead environments on Earth, Death Valley, California. Even in Death Valley, little clumps of vegetation and surface oases manage to survive. Groundwater collects in deep underground voids along tectonic fault lines. As the rocks shift and crunch together, they build up immense pressure, forcing that trapped water up through tiny cracks all the way to the barren surface. A similar subterranean plumbing system could be driving the seasonal streaks on Mars. Mars experiences severe climate cycles, including ice ages that last 100,000 years. To see if life could survive that kind of freeze, microbiologists sampled the Bonneville salt flats in Utah. They found living 97,000-year-old bacteria trapped inside tiny fluid pockets within the solid salt crystals, proving that microbes can easily hibernate through prolonged deep freezes. This capacity for extreme endurance suggests a potential blueprint for Martian survival. Instead of active organisms on the surface, researchers look for life suspended in a deep freeze hibernation underground, waiting for a geological event to release it. For decades, astronomers focused their search on the so-called habitable zone. The habitable zone is the specific distance from a star where a planet is just warm enough to maintain liquid water on its surface. Today, that rule is largely considered outdated. Consider Enceladus. It is a tiny, freezing moon orbiting Saturn, roughly 745 million miles outside our Sun's habitable zone. With surface temperatures dropping to 330 degrees below zero, it should theoretically be a dead, solid block of ice. Yet the Cassini probe photographed massive geysers shooting out of the moon's south pole. As Enceladus orbits, the massive gravitational pull of Saturn constantly stretches and warps the moon's rocky core. This intense friction generates enough internal heat to melt the ice from the inside out, creating a massive, warm, subterranean ocean. Evidence of internal oceans shifted mission objectives toward the Martian interior. NASA's rovers now use ground-penetrating radar to search for these hidden, briny habitats where microbial life is most likely to thrive. The search for extraterrestrial civilizations also involves direct interstellar transmissions. In 1974, scientists used the massive Arecibo radio telescope to broadcast a concentrated, highly structured message deep into the cosmos, hoping to catch the attention of anyone listening. The universe is far more chaotic, violent, and bizarre than our early, orderly models ever suggested. By chasing down its impossible glitches, from geometric storms to raining rubies, we have finally learned exactly where and how to look for our cosmic neighbors.